As we saw in the previous lectures, since the early formulation of the principles of quantum computing, many quantum algorithms have been designed and programmed to provide a significant speedup compared to their classical counterpart. Many algorithms, such as Shor's algorithm, Grover algorithm, have many applications in security, in data search, machine learning, and designing new materials and developing new drugs. Current quantum computing experimental platforms are complex and hard to operate. Therefore, when designing new algorithms, one of the main challenges in the field of quantum computing is the implementation of those algorithms and their execution on a real quantum computer, or answering simply the question, how to program a quantum computer. Programming a quantum computer requires that the quantum computer to be programmable in the first place. And that means that it should have a microarchitecture capable of executing instructions. So the user can write his algorithm using a high-level language, such as the OpenQL language, compile it to transform it, the human-readable code, into an executable code, and execute the produced binary code on the quantum computer hardware. To achieve that goal, a lot of work has been done in QTech to design the microarchitecture, which accepts a well-defined set of instructions and execute them to perform the quantum operation on the qubits and acquiring back the results of that computation. The microarchitecture is responsible of executing both the quantum operations and the classical ones, which compose usually a quantum algorithm. The quantum instructions are ultimately translated into microwave pulses, which are sent to the qubit through a digital to analog converter, and the measurement acquisition through an analog to digital converter. We will present the microarchitecture details in the dedicated lecture, but for now, let's assume that we have such a programmable architecture. To allow the programmer to express his algorithm easily, we need a high-level language or high-level programming language which abstracts away the low-level details of the machine and offer a friendly programming interface for the user to write a human-readable code and to express those algorithms. Many research labs propose different quantum programming language and framework, such as Scaffold from the University of Chicago, or Project 2 from ETH Zurich, or Liquid from Microsoft. Here in QTech, we have designed the OpenQL framework, which allows the programmer to write his algorithm, including the quantum and the classical part. Like OpenQL follows a heterogeneous programming model, where the quantum computer is considered as an accelerator, and the general-purpose processor is used as the host processor. OpenQL supports two high-level languages for now, which are C++ and Python. Let's now consider the Shor's factoring algorithm, which is an example of a quantum algorithm which allows finding the prime factors of a large number and offer a significant speedup compared to classical implementations. As we can see, the Shor's algorithm is a mix of classical instructions and quantum instructions. For instance, computing the greatest common divisor of two numbers can be done efficiently on a classical processor, while the quantum Fourier transform, or the QFT, and other quantum operations can be done by the quantum processor. To transform these human-readable quantum algorithms into an executable machine code, we need a compiler. The job of the compiler is bridging the gap between the quantum algorithm, or the software, and the quantum hardware by transforming these algorithms into quantum operations, optimizing them, adapting them to the target quantum platform. The compiler transforms a human-readable code into a quantum assembly code, then into a binary executable code. In the next part, we will see how this compiler is designed and what are the different stages of transformation which are applied to a program to make it executable on a real hardware.